Continuing on physical chemistry, chapter 9, we're in section 8 now. We're going to be talking more about ideally dilute solutions. Now, for one thing, the concentration of the solute is so low that we can just say that the mole fraction is roughly equal to the molality, which is roughly equal to the molarity, just because they're all roughly zero anyway. So the chi is the mole fraction, remember, m subscript I is the molality, and then c sub I is the molarity. So remember, the chemical potential of the substance I is equal to the chemical potential of the substance I in the standard state at whatever temperature and pressure, plus RT times the natural log of the mole fraction of the substance I. And in this case, we could just rounding instead of use mole fraction, molarity, or molality, or whatever. It'll still come out pretty good. So let's talk about vapor pressure in an ideally dilute solution. So we have this system. Up here we have the vapor pressure, so P subscript I is going to be the partial pressure of the substance I. And then of course down here we have the liquid solution, which has both the solute and the solvent in it. And then of course P is total pressure. So we have the chemical potential of the substance I in the vapor phase. That's equal to the chemical potential of the substance I in the vapor phase in the standard state at whatever temperature, plus the gas constant R times the absolute temperature times the natural log of the partial pressure of the substance I divided by the standard pressure. That way there's no units in the natural log. And this is assuming an ideal gas mixture. Then the chemical potential of the substance I in the liquid phase is equal to the chemical potential of the substance I in the liquid phase at the standard state, whatever temperature, plus the gas constant is R times the absolute temperature times the natural log of the mole fraction I in the liquid phase. And this is in the solution, of course. Now remember, if we're at equilibrium, or at least phase equilibrium, then the two phases have the same potential for each substance. So like the chemical potential of the substance I in the liquid phase has to be equal to the chemical potential of the substance I in the vapor phase. So substituting these down here, we end up with the chemical potential of the substance I in the vapor phase at the standard state plus the gas constant R times the absolute temperature times the natural log of the partial pressure of the substance I divided by the standard state or standard pressure, and that's equal to the chemical potential of the substance I in the liquid phase at the standard state plus the gas constant R times the temperature times the natural log of the mole fraction of the substance I in the liquid phase. Then just doing algebra, we're going to rearrange stuff around here. So we end up the chemical potential of the substance I in the liquid phase minus the chemical potential of the substance I in the vapor phase. And that's equal to minus the gas constant R times the absolute temperature times the natural log of the mole fraction of the substance I in the liquid phase plus the gas constant R times the temperature times the natural log of the partial pressure of the substance I divided by the standard pressure. Now we're going to divide both sides by R, so doing that literally we'll just end up with chemical potential of the substance I, the solute, in the liquid phase at the standard state minus the chemical potential of the solute in the vapor phase at the standard state divided by RT is equal to minus RT times the natural log of the mole fraction of the substance I in the liquid phase divided by RT plus RT times the natural log of the partial pressure of the solute divided by the standard pressure divided by RT. Rearranging and then obviously canceling around. And remember, when you distribute a minus into the natural log, it turns it upside down. So anyway, we end up with mu, the chemical potential of the substance I in the liquid phase at the standard state, minus the chemical potential I in the vapor phase at the standard state, divided by RT, and that's equal to the natural log of the partial pressure of the substance I divided by the mole fraction of the substance I in the liquid phase times P naught. Now we're going to take E to both sides, the natural number E to both sides. So we end up with the partial pressure of I divided by the mole fraction of I in the liquid phase times P naught is equal to E to the chemical potential of the substance I in the liquid phase at the standard state minus the chemical potential of I in the vapor phase at the standard state divided by RT. Now remember, We have the chemical potential of the substance I in the liquid phase at standard state at whatever temperature and pressure, and the chemical potential of the substance I in the vapor phase at the standard state at whatever temperature and pressure. Now this is a little bit pressure sensitive, but it definitely is temperature sensitive. The reason is because we have temperature up there in the exponent, right? So we're going to simplify here by combining some terms. So basically we're going to move this P naught over here and define all of it as one big term. So we're going to define this K as P naught times E to this whole power. Chemical potential of the substance I in the liquid phase, standard state, minus chemical potential I in the vapor phase, standard state, divided by RT. Now this is P naught divided by mole fraction of L. That's equal to Ki. So see what we did here? We substituted this K for all that into the original equation. So this Ki would be, the K for this particular solute. This formula here is called Henry's law. And remember, because of the what we did was for an ideally dilute solution. So Ki is Henry's law constant. It is dependent on both the solvent and the solute. And if you notice, because of the way we calculated it, P naught in front of it, the units are going to be in units of pressure. So we have the partial pressure of I is equal to Ki times the mole fraction of I in the liquid phase. This here is actually Henry's law. It's just rewritten. We solve for pressure. Now this is good because you can use this formula like when you want to dissolve a gas in a liquid. Now we remember, though, we assume the solute is in an ideally dilute solution and that we have an ideal vapor, but we can kind of use it to carbonating liquid, which is a little more complicated than ideally anyway. Now this only applies to closed systems, though, because of the partial pressure thing. And of course, like I mentioned before, it only applies to electrolytes because you don't have electrolytes in an ideally dilute solution. Now if you look at the algebra, then you'll notice that as pressure increases, that means that the mole fraction is going to increase, and therefore the solubility is increasing. Now mole fraction of I is dimensionless, and so the Ki also has units of pressure, just like I said before. Now like for hydrogen gas as the solute with water as the solvent, Ki is about 71.7 kilobars. Now for hydrogen as the solute and benzene as the solvent, Ki is only about 3.93 kilobar, 1,000 bars. Now remember, though, a lower Ki has higher solubility because you notice the mole fraction is equal to pressure divided by Ki. Now likewise, carbon monoxide, argon, oxygen, nitrogen, methane, and what is that? Oh shoot, I forgot. Whatever that molecule is. It's also more soluble in benzene than in water. So the partial pressure P sub I is equal to Ki times the mole fraction of I in the liquid phase. That's assuming the solute obeys Henry's law, and that's for an ideally dilute solution. Now Pa is equal to mole fraction of A in the liquid phase times Pa star. That means pure, right? That's what happens if the solvent obeys Raoult's law. Now let's talk about variation of gas solubility with temperature. Now generally speaking, if temperature increases, that means the mole fraction decreases, and therefore solubility for water, but then again it's the reverse for organic solvents. So if you have increasing temperature, that means increasing solubility, increasing mole fraction, increasing solubility when you have organic solvents. Although generally speaking, when you have temperature increasing, that means stability is decreasing. Now remember, though, I mentioned several times already, Henry's law does not apply to strong electrolytes such as HCl gas. Like you have HCl gas and put it in water, H2O liquid, it doesn't just dissociate, it becomes like these hydronium ions, aqueous, and then the chloride aqueous ions. So the Henry's law doesn't even apply there. It's something totally different going on. Now Henry's law also does not apply when the solute, the gas, reacts with the solvent. For example, let's say if we have ammonia gas and H2O liquid, you're going to get ammonium hydroxide. So NH3 is very soluble, but it's different from an ideally dilute solution. So likewise, if we have ammonia gas plus H2O, it's actually in equilibrium with these ammonium ions and then the hydroxide ions. Now helium is even less soluble than nitrogen in water, which you kind of expect because, you know, it's a tiny molecule and no polarity at all. Now the chemical potential I is equal to the chemical potential of I in the standard state plus the gas constant R times the temperature times the natural log of the mole fraction of I. That's for non-electrolytes. Now here's a graph showing you what's going on. So at the bottom here we have increasing pressure, like 100, 200, 300 atmosphere. Over here we have the mole fraction of the nitrogen or the mole fraction of the hydrogen. Now Henry's law is a straight line. That's this dotted line here. But you'll notice for N2 it starts out a little bit following Henry's law, and then once it gets like up to 100 bar it deviates down. So it's only linear to about 100 atmospheres. Hydrogen, it goes up linear about 200 atmospheres and then it levels down. So this is why Henry's law, it really only applies in an ideally dilute solution, which means low concentration of the solute, obviously. Now real substances, they have a curve instead of a straight line because Ki isn't really a constant with changing pressure. It changes. Now let's say we have the pressure of the solvent. That's equal to the mole fraction of the solvent in the liquid phase times Pa star. So the partial pressure of the solvent in the pure state. That's Raoult's law. So here we go. This is a mole fraction on the bottom. So 0 chloroform up to pure chloroform, and the rest is acetone. So 0 acetone to pure acetone. So basically we're going to be starting out with pure acetone and then increasing the amount of chloroform as we go left to right. And then up here we're going to have the pressure above the solution, the partial pressure above of the substance above the solution. So for the pure substance acetone, you have whatever pressure is. This is the partial pressure at this temperature of the acetone. And over here, you have the pure, the pressure of the chloroform in its pure state. So the dotted lines show you the ideal here. As you just increase, it's going to stay straight. Or same thing, following Raoult's law, it's just going to go straight up like this, or straight down like this. But in real life, these curves show that there's negative deviation, which means it's lower than you would expect based on the laws. Now the reason has to do with shape. Let's take a look at this. Here's an acetone molecule. It's a ketone, so you have the oxygen hanging off here. And then chloroform, see it's, trichloromethane, I guess how you'd say that. See a bunch of chloroform. So think about this. The oxygen, the nitrogen, and fluorine are the most electronegative. So oxygen has an electronegative 3.5, and then fluorine is 4.0. Now hydrogen bonding, remember it's intermolecular bonding, where you have X, like carbon or whatever, with H coming off, and then hydrogen bonded to Y. So X and Y are either like oxygen, nitrogen, or fluorine. Oh yeah, obviously not carbon, that'd be just methane. Yeah, so this would be like an OH or an NH or an FH, whatever. So think about this. Acetone is not technically hydrogen bonding to chloroform, but it kind of behaves like it. Because you see, on the oxygen, there's no H coming off, so it's not really hydrogen bonding. But in the H in the chloroform, it is attracted to unbound electrons in the oxygen and the ketone. So that acetone and the chloroform, they bond to each other better than to themselves. You see, that's the thing. You have a whole bunch of this stuff here. They've got all the free electrons, or not free electrons, but unbound electrons here. So they'll just bond to each other like it's nonpolar. Same thing with the chloroform. There's not, but when you have the these two near each other, then the oxygen and the hydrogen, they try to bond with each other. So that's the negative deviation. They bond with each other. Here's the diagram showing it. So the hydrogen here is attracted to these electrons on the oxygen there. So it's not really a hydrogen bond, but it's similar to the hydrogen bond. It's a strong bond. That's what causes that negative deviation. So because chlorine is so electronegative, this carbon atom here in the middle of the chloroform, it's highly electron deficient. So the hydrogen, it gets a partial positive charge, which makes it even stronger to bond with the electrons in the oxygen. Oops. So here's a different example. This is CS2. I don't even know what you would call that substance. Oh, carbon disulfide. Okay, so here's the same thing. We're starting out with pure acetone, and we're adding this carbon disulfide. So at either end, we have the partial pressure, the pure acetone, or the the pressure of the pure carbon disulfide, right? And again, these straight lines, this is what the Raoult's law and so on would predict based on a perfectly straight line. But this one has positive deviation. The reason is, of course, simple. This carbon disulfide molecule, it has no polarity at all. It's just, straight. There's no... But here, this one, because of the way the oxygen comes off one side, it's sort of polar. So when you have the polar and the non-polar, they don't want to bond with each other. They want to just keep to themselves. So we have positive deviation in this case. So the pressure is greater than what you would expect if they were separate. Okay, that is the end of Chapter 9, Section 8, and that's actually the end of Chapter 9, too.